Swayam Prabha. Digital India. Educated India.
About a very generic strategy of designing algorithms, which will be applicable for most of the problems that we talked about yesterday. But I will not take them up individually. I'll take a couple of examples, and then there is a nice generalization which I will point out, and there's also a very general analysis for that framework, which I will give you some glimpse of, but I may not be able to complete the entire analysis. Right? So with that short introduction, so let me get started with a problem that I'm sure all of you are familiar with, that is given a set of points P. Find the closest pair. That's for the closest pair problem. So essentially what you're doing is that this is same as minimum over all ij distance pi j. So I'm sure all of you must have at some point encountered this problem, either as a simple programming exercise or in some algorithm course, whatever. The challenge, of course, is not just to solve the problem, but solve it efficiently, right? So naive approaches so maybe I should write argument, because actually I'm trying to find out ij that minimizes the pair. So naive approaches would be what? Try all possible pairs ij, sorry, which basically means that n choose two pairs let's say distance computations, right? What are we doing? We're basically looking at every pair and computing distance. So the good thing about this very simple algorithm or naive algorithm is that it doesn't matter what the distance function is. So we can use Euclidean distance, L2 norm, L1 norm, whatever dimension, right? So the naive algorithm will work across all possible LP metrics, all possible dimensions. Right? But problem is that this n choose two computations, which is basically saying about n square. Okay, if I can compute the distance between 2 points in constant time, so we can always do this simple. So distance function can be computed you don't even have to compute the square roots basically, because I can work with the squares of distance also. If you're looking at Euclidean norm, so I don't need to even look at square root. I don't need to compute a square root. I can work even with the distance squared actually. That will suffice. So order n square is the time complexity for this algorithm. So question is that can we do better? And how much better? So this, let's first look at a simple one-dimensional case. Okay, suppose all the points were in one dimension. So here is the line. So all points basically appears on the line, and let's assume that we have. So these are, let us say, in sorted order. Of course, it's not given to us in sorted order, but I'm just giving you a picture of what this could look like. Okay. Points are not given in sorted order, and even if it were given in sorted order, it's only going to work in one dimension. Like in two dimensions and higher dimensions, there is no notion of sorting the way that we do it. Okay. But let's say in one dimension we are given this set of points, and we want to find the closest pair. So one simple observation that we can exploit is the following: the closest pair must be a consecutive pair, right? So if we sort the points, then the closest pair has to be one of the consecutive pairs. So the number of candidates, okay, so number of so-called candidate pairs are pi plus 1, okay, where pi are sorted. So alternately, we can sort the points. Okay, so first sort points, and then try the n minus 1 consecutive. And then what will be the running time of this algorithm? N log n, because sorting takes whatever time. Let's say sorting takes n log n time. Sometimes you can even do faster sorting if the points are integral points and things like that, right? Integral points in a bounded range, you can use radix sort, etc., and you can do it. So basically the whole thing is dominated by the sorting, because the next part, there are only order n distances to be computed, right? So time complexity is dominated by sorting, whatever it is. So let's say then certainly you can do it in n log n time. Right? So you can see from this n square, the naive algorithm, we could make a leap into the n log n. Reduce it to the n log n bound. Now, having succeeded on that, you could be more ambitious and say, oh well, maybe I can do even better, right? But the even better thing, unfortunately, the bad news is that omega n log n is a provable lower bound for this is a problem called element uniqueness. I don't know, this is a prototype problem for proving lower bounds. So element uniqueness basically is a problem that says given an elements n, is there a pair, or let's say are all points unique basically. All points unique, that is xi not equal to for all. So this is a decision problem. It's a very simply stated problem. I give you a set of numbers and I ask you, tell me whether or not there is a duplicate. That is what I have defined. given n elements are all points unique, that all points are distinct. Okay, maybe distinctness, sometimes called distinctness is fine. That's a better term maybe. So, this problem has been well studied, and it is possible to prove a lower bound of n log n. Of course, it will define the model of computation precisely, but in fairly strong models of computation, algebraic model of computation, which I am not going to get into this at this stage, it is known that you cannot do better than n log n. So, if you can't do better than n log n for element uniqueness, okay, clearly we can't do better than n log n for closest pair, because element uniqueness can be reduced to closest pair, right. So, since element, let us call it distinctness, so this is called reducible, okay, reducible to closest pair. The lower bound also applies. Otherwise, we could violate the lower bound. I will just find out what is the closest pair, and if the closest pair distance is 0, then they are clearly not unique, and vice versa, right. So, I will just point it out. Non-distinct. So I can't do better than that. Fine. Okay. So we have achieved our goal in one dimension. Sort it, scan the elements, look at every consecutive pair, and keep track of which is the smallest gap basically. By the way, since I mentioned this thing called gap, so instead of the closest pair, suppose I am looking for what is called the largest gap. Seems like a very related problem, right? So, again in this sorted set of elements, which is the largest gap that you have? Closest pair is the smallest gap, and I am saying the largest gap. It turns out these are some very non-intuitive things, that the largest gap actually has a faster solution. Okay, I will not discuss that, but you can try it out. It's a nice toy problem. Note, there is a simple order n algorithm for the largest gap. So it looks like as if there are symmetric problems, but they are not. So it's easier to solve the largest gap than the smallest gap. Closest pair is like the smallest gap. Fine, so far so good. So made some progress, but then again we have not solved something non-trivial. In one dimension, how often are you going to solve closest pair in one dimension? Okay. So in the least we are interested in solving it in 2 dimensions. Okay. That's the problem, right? So I am given these points. So now I am challenged. Okay. So I am given points in 2 dimensions. It could be in 3 dimensions, it could be in even higher dimensions. Now what do I do? Is there any possibility that I could extend the algorithm that we use in the 1 dimension? Unlikely, because we can't sort. There is no notion of ordering or sorting in 2 dimensions. I mean, there are some ways that you can define a certain kind of ordering in higher dimensions, but those are not as simple as some number is less than some number. So often the kind of ordering people use for higher dimensional points is that you look at basically a plane defined by the D points and another point and look at the orientation, okay, whether it's above or below. So, if you have that information for all possible D+1 points, that's some kind of ordering. In fact, that ordering kind of also follows from the arrangement. So, if you know the arrangement, you have some kind of ordering, but it is not as simple as linear ordering. It carries enough information, and that's that trying to construct an arrangement takes n to the power d time in d dimensions. So, that's not going to work for this kind of problems. Well, ordering basically means greater than smaller than, right? It's a linear ordering. So, in the arrangements there is no such unique ordering, right? As the lines intersect, the ordering changes. So, you look at any vertical cut, the ordering actually changes, but it carries all the information about the points. But that will be an overkill, trying to construct an arrangement to solve a closest pair or any other problem is usually an overkill, because it's very expensive, n to the power d, and that's not even polynomial time if d is not fixed. So, how many of you have actually come across this problem of solving closest pair in 2 dimensions? Yeah, okay. So, many of you are familiar, and I suspect that so some of the standard textbooks nowadays describe an algorithm for closest pair, and you often, I think, if I were to guess, you probably use some kind of a divide and conquer algorithm. Okay, yields an n log n algorithm, okay. And very simply stated, basically you divide the points into 2 parts using a x bisector or something. So, look at all points less than the median x values, you partition it 2 parts, solve the problem, find the closest pair here. On this side, closest pair on the other side. Suppose this is delta 2 and this is delta 1, okay. Now, how do you combine them? You need to merge them. When you merge them, that's the tricky part, because then you have to do something like actually compare across points across the boundaries, because you have not looked at those things, right. And for that you need to use some geometric arguments, that how many points basically can be very close in the boundary, given that on one side the closest pair is delta 1 distance, the other side the closest pair is delta 2. So, how many points basically can be close across this line that you need to compare. So, eventually it comes down to again using some geometry or some kind of packing arguments basically to get to a recurrence like t's of n equal to t's of 2 times t's of n over 2, because you have solved the problem for the 2 halves, and then for combining you need that argument on packing to show that there is no more than order n pairs that you have to show, then the merging can happen in order n time, and that yields the n log n algorithm. Okay. So, this some of you are familiar with and others are not, but you can guess basically. But the tricky part really is how do you merge, okay. How many points across the boundary do you need to compare, right? I need to compare this point with this point, this, but probably this is not required, they are really far apart, okay. So, because this delta 1 and delta 2, you can confine yourself basically to some boundary like around this, some portion of some width which is not more than, you do not have to go very far, right. Sorry. So, this, why is it automatically moving? When I move my hand, the screen seems to be automatically scrolling. So, you need to basically look at points within this narrow width of maybe delta, that is minimum of delta 1, delta 2. Okay. Because any points that are further apart by that cannot be closer than delta 1 and delta 2. We already have pairs that are closer as close as minimum of this. So, within that thing, so basically then you have to show how many points can occur within that narrow slit, and there will be like, so with some argument you can show its order n and you are done. Then you can do the merging. Okay. So, I am not going into further details.